Okay, hey guys, welcome back and Happy New Year. So I thought we'd start off in 2015 with a quick video on oscillations, so just recapping some of the basics that we finished 2014 looking at. And the first thing just to go through is the basic rules of SHM. If you can't remember what that is, SHM stands for Simple Harmonic Motion. And that's the sort of basic kind of motion that all oscillating bodies undergo, as long as they abide by three simple rules. Everything we're going to consider today is going to be for a system like this. So here I've got some horizontal frictionless surface, and that's important, so that the only thing acting on this mass here is the spring. So horizontal setup, spring attached to a mass, and I can set this going and it will oscillate in the X plane. Few things to define here. I'm going to call this this position, X equals 0, the equilibrium position, so that's EQ with an M superscript underlined. And that's special because that equilibrium position is the point where there are no forces acting on my block, and therefore it experiences no acceleration at that moment. Okay, so going back to our rules, like I said, there are three basic rules, and one of them really is kind of an aside, and it's an aside for when some of you go and do big boy physics at university, so I'll come to that in a sec. So considering the system, three rules. First rule is a nice simple one. When I set this off, this should undergo motion which is periodic, so the motion must be repeating or periodic. And that is to say that there are no sort of special instances in time. It's a frictionless system, so I can look at it now and it will be doing this regular motion. If I came back in 20 minutes time, it would look identical. If I came back in 100 years time, it would look identical. So it's just some repeated motion, which is sort of independent of time, if you like. That's not a good way of putting it, but it doesn't matter when I'm looking at it, that motion looks the same. The second rule, so if you like, it's just going round and round, or mathematically, as we'll see in a minute, it's going to be some sinusoidal, so sine or cos function. The second rule, number 2, more important rule, and this is the thing that gets asked most often, is that A, my acceleration at any given point for the mass is proportional to x, and it points in the opposite direction. So if we consider some time later, my mass might have moved over here, so there's my spring. We could consider a position vector x underlined, and there will be some acceleration vector a underlined acting on it, and it's always in the opposite direction. If I increase x, a will also increase in step. Likewise, if I decrease x, so will a. So in words, what this is saying is that acceleration, the acceleration experienced by the mass is proportional to x, so it's proportional to position, and importantly, its vector, so the acceleration vector always points in the opposite direction. And what that means is that acceleration that acceleration vector always, and I'll underline that because it's important, it always points to equilibrium, EQM. So that's rule number 2. These vectors are always proportional and opposed, and we'll see that coming into play in a sec. So let's get rid of that. And the final rule, which is kind of, like I said, it's just an addendum, if you like, it's just an added convenience. The third rule is that oscillations must be small. in amplitude. And the reason why I say this is sort of an aside, it's a sort of extra rule, is because this rule, number 3, ensures that this rule happens. Like I said, some of you, when you go to do physics at university or modules in oscillations in university, what's happening is you can consider if I don't have this statement being true, so if my oscillations are very large, now what's going to happen to my spring if I force its oscillations to be incredibly large? Obviously, then we're going to have some problem because we're going to go beyond the elastic limit, and therefore Hooke's law is no longer going to be true, and therefore this guy is not going to be true either. So really that third rule is just to ensure that the second rule is in place. And if you like, you can work your way backwards here. 3 ensures number 2, 2 ensures number 1. So there's our basic 3 rules. Okay, so something we might be interested in if we consider our block, we're actually interested in the equation of motion for this bad boy. And it's really simple to do, actually, really easy. So let's consider stretching this mass to a position at x, and let's consider the forces acting on it. So we said frictionless surface, the only force acting on it is going to be due to the spring, and we know that that force F is just due to Hooke's law. So we've got F is equal to minus kx. This is a body in motion, it's a mass, it will be accelerating, so we also can invoke my boy Newton's second law. So this is a bit of Newton 2 here. So we can also invoke F equals ma, and with a trivial little bit of rearranging, I can rewrite this as A is equal to minus brackets k over mx, which is good because we can see straight away this links back to rule number 2. So we know that this setup we've got here will follow SHM as long as I'm within the proportional limit of my spring. So there you go, first sort of really simple equation of motion, and I'll chuck a little box around that because that's quite neat. Okay, there you go, so basics done. So something else we want to look at is some equations, or some graphs I should say, for this motion. So the first thing we can look at, we'll look at a few graphs. I don't want to spend too long in this video, I just want to do the basics. But one graph we can look at is this graph here, so the graph from this equation of motion, and that's a pretty standard graph. So if we plot acceleration against position for this, we know they're proportional, so it should go through the origin, should be a straight line. It's also negative, which means it will be backwards, and that does not go through the origin. Let me just sort that out. So our line will look something like this. If you wanted, you could pick out the gradient. The gradient would be equal to k over m. So, you know, basic questions they could give you here is a graph, and they could ask you to find k given the mass or something like that. So our oscillator in its lifetime is basically going to just boing back and forth along this line, so it's literally just going to do this back and forward along that line. A very meaningless existence, pretty boring. But something a bit more interesting from this is we can pick off some maxima along here. Now we know that we've got some A max here and some minus A max, if you like, some A max in the opposite direction, and these come from when our mass, if you like, is here at 1 amplitude and another extreme point over here at its positive amplitude, and hopefully if this is at SHM, our equilibrium position will be slap bang in the middle of that. So we can look at our equation of motion up here and we can see that, well, when is my acceleration maximized? Well, it's pretty simple. The maximum value that position can have is obviously the amplitude by definition. So that means my maximum accelerations are going to be at plus and minus k over m times a. So if you like, that's another nice little equation of motion that we can use there. So what we've got here then is we can just draw those on. A max is equal to plus, if you like, k over m times a, and this will be equal to minus k over m times a, and these will be found at the positive and negative amplitudes respectively. So that's a really simple graph we can look at, an acceleration against position picture. Okay, so pretty boring. Let's go a bit deeper. Let's consider the actual motion. So the simplest thing we can do in terms of motion is look at its position as a function of time, because even looking at this is a sort of static picture, it's a snapshot, and really what we're interested in is how does this evolve over time. And because of these rules, particularly because of the second rule, one solution, and again, if you go on to do physics at university, you'll look more deeply at this, but one solution to this statement is to have a function of x which looks something sinusoidal. So I'll just draw one period, so that abides by my rules up here. So any oscillator undergoing SHM should do something like that. So what equation does that follow? That's what we're bothered about. So mathematicians, you may like to write it like that. It's position as a function of time, but I'm going to ignore that just for simplicity. We know that this guy should, at its maxima and minima, be at the amplitude. We know it's going to be some sine function, and we know it's going to be some function of time. But the more complicated thing here is that well, the first thing is, mathematically, when we look at this, the sine has, at the moment, an argument which is, or has dimensions of time. We can't have that. So really what we want to do is make sure that inside this bracket we have something dimensionless. So a nice thing to do is to divide by the time period. So if we denote this as one time period, I'll just label it as t there, then that's a nice way to do it. But we also want to make sure that when t is equal to the complete time period, we want to make sure that this function x equals 0. We also want to make sure that when t is equal to half a time period, x is equal to 0. And we want to make sure that when t is equal to 0, x is equal to 0, so that it follows this function here. We want to ensure that these 3 points, and in fact, more broadly speaking, these points as well, are where they should be. So we also want this maxima amplitude and this minima down here. And the way we do that is by simply inserting a constant into my argument, and that constant is 2 pi. Now I'll let you play around with that, but you can see now that when t is equal to 0, then this argument goes to 0, and therefore x is nothing. Sine of nothing is nothing. When t is equal to the time period over 2, that's going to cancel, and the half here is going to cancel with the 2, and therefore that's going to give me sine pi, which brings us back there. I'll let you just figure out for yourselves that this does in fact give us this maxima at the amplitude and minima down there as well. But all I'm going to do is, I don't like this. A neater way of writing this is by saying that 1 over time period is equal to frequency. So I'm going to get rid of that, and I'm going to write it that way instead. It's a bit more convenient mathematically. Okay, so this is my basic function. And now what I want to do is look at what happens when we look at velocity and when we look at acceleration. So let's look at velocity first. So v on this axis, t on this axis. Mathematicians, you could, if you like, say that v is the time derivative of x, and that will give you a 2 pi f cos 2 pi f t, and I'll let you go prove that. What we're interested in is, obviously that's going to look like this, but physically, why does it look like this? So you can see this is out of phase by 90 degrees. So really what we're saying here is that our velocity is maximized when my position is at equilibrium. So if you like, 0 here is my equilibrium position. My fastest speed occurs at equilibrium, and that makes sense because at equilibrium I have no longer any force, no longer any acceleration pointing in the opposite direction to the motion. So it makes sense that that's going to be our maxima. Finally, what we can look at is how the acceleration itself behaves with t. And we're expecting that a is proportional to minus x. So we're expecting a sine function again, but a sine function which is reflected. So if I go back up here, it's reflected about the t-axis, so that it follows this behaviour from rule number 2. And again, mathematicians, if you like, you can say that acceleration is the time differential of v, and that will give you 2 pi f squared sine 2 pi f t. And I'll let you prove that to yourself. And that's nice because, again, if you do that, you can see here that a times sine 2 pi ft is actually just x, so that gives us a is equal to minus 2 pi f squared x, which follows the rules we were after, which is great. And just some things to point out again, obviously at equilibrium, so when x is at equilibrium here, here and here, my acceleration is 0, as it should be. When x is at the amplitude, a is maximized in the opposite direction, and the same up here. Okay, so that's the basics of oscillations. The next video, what we'll go through is we'll just look at a few things. The first thing we'll do, that's just while I'm thinking of it, we'll derive from this how to calculate the time period t of any SHM, any body undergoing SHM, and we'll also look at energy and damping. So TED. That's what we'll do next video. Hopefully that'll be coming soon, but for now, thanks very much for watching. I'll see you guys later.